Welcome to our last part of our course on the Internet of Things. So, in these final three lectures, plus the summarizing lecture at the end, we're going to talk about the topic of energy in the IoT. And today we'll start off with how to model power and energy in systems, how to analyze this, and which energy sources are usually available on IoT systems. So, power and energy play a very important role in the Internet of Things. And the challenge is to enable IoT edge devices, so all these small devices that are running somewhere out there, running sensors, running actuators, collecting data, whatever you can imagine, and of course, collaborating on wireless networks. We want to enable them to conserve energy as far as possible so that we can run them as long as possible with a depletable energy source that is just, yeah, finite instead of an more or less seemingly infinite energy source, like, well, being connected to a wall outlet. So this means that very often we have to run these devices with unreliable energy sources. They can be intermittent, so depending on, for example, availability of sunshine, if you use solar cells as an energy source. And in general, this way of collecting energy for an IoT device, so little amounts of energy that are just enough to operate your IoT device for short amounts of time. This is called energy harvesting. So, some questions we need to ask ourselves in order to achieve this are: how can we assess the power and energy consumption? Because that's the first step for what we consider in our next lecture, how to optimize the energy consumption. We need to know which components influence power and energy consumption. And of course, we need to get an idea of how we can harvest energy from the environment. So, if we look at CMOS semiconductors, which are at the heart of most electronic components we use today in the IoT, we actually first need to look at the power that's dissipated by the device. So power is voltage times current multiplied, and the power dissipation in semiconductors actually can be more or less classified into two parts that play together. One part is what we call the static power dissipation or leakage power due to subatomic effects, for example, the tunneling of electrons in areas of the semiconductor where an electron shouldn't actually occur. This is a subatomic effect that is more and more prevalent with lower sizes of semiconductor structures. So we're always continuously lowering or trying to lower the sizes of semiconductor structures to put more transistors on a chip. And the smaller our transistors, our conductors on our semiconductor become, well, the higher these effects of static power dissipation are going to be. These are subatomic effects which are mostly independent of the frequency we operate the circuit on and of the switching, so how often we switch a value from 1 to 0 or back. And the static power dissipation in turn is mostly dependent on the voltage we supply our semiconductor with and the voltage our semiconductor switches with, so the supply and the threshold voltage, and also the relation of the geometry of the transistor, so of its width W and length L. So our static power dissipation is a function of the supply voltage, the threshold voltage, and uh, the fraction of the width to the length of a transistor on a chip. The other kind of power consumption or power dissipation in a semiconductor is dynamic power dissipation. And this is power dissipation that we actually want to take place because this is needed to switch values from 1 to 0 or the other way around. So in order to change a state in our semiconductor, so to change data, for example, because we want to add two numbers to a result, so we switch bits from 1 to 0 and back in the result, we need to move electrons across the chip, and essentially this switching power happens we switch between logic levels ones and zeros, so we move a charge across the chip, and when this happens, we have temporarily very short-timed short circuit conditions from supply to ground when, for example, in an inverter, both transistors, the one going to the supply voltage and the one going to ground, are active at the same time. Maybe just for a fraction of a nanosecond, but still there can be a very minimal current flowing, which, yeah, just participates in this whole dynamic power dissipation. And the dynamic power dissipation now is dependent on the frequency with which our chip at, and usually the square of the supply voltage. While the square is an approximation, for modern semiconductors, some experts believe that it might actually be the cube of the supply voltage already. So the dynamic power consumption is proportional to the frequency times some capacitors of a chip times, let's assume it's the square of our supply voltage. So the higher our frequency, the higher our supply voltage is, the higher our dynamic power consumption becomes. So if we clock a chip faster, then we increase our dynamic power, and it gets even worse because in order to clock a chip faster, we have to supply it with a higher supply voltage usually. So we have not only the frequency contributing to this increased power consumption, but the voltage goes in as a squared value even. And in turn, the total dissipation of power is then the sum of our static and our dynamic power dissipation. Right, so this is power. So this is what momentarily happens at a chip at every given point in time. Now, there's very often a confusion between power and energy. So we need to look at energy now. So what's energy? Now, energy is just adding the power up over time. And since power can change at every instant, and not only in fixed intervals, we are not adding fixed amounts of power up, but we're using the mathematical approximation where these time intervals we add up get smaller and smaller, so we use a limit value towards zero. So in turn, we calculate the integral over our power consumption over a given amount of time to obtain the energy. And the energy is what we store in a battery. So a battery has a capacity of so and so many joules or watt hours, which is the same unit. And in turn, this means, yes, if this energy is used up because our energy consumption, so the integral over our power over time, well, reaches the capacity of the battery, and then of course we have some losses in transmission and so on, then our system has to shut down because we've run out of energy. So power and energy models become increasingly important because we have mobile applications, we have IoT applications, obviously. Energy availability is more relevant because we have increased performance, so increased power consumption, in turn, increased energy consumption, and of course, also due to environmental issues, uh, because some forms or sorts of energy rely on non-renewable resources of the Earth, which is not a good idea. And this includes non-rechargeable batteries, which, for example, might contain lithium, which is only available in very limited amounts on Earth and mostly used for car batteries right now. Now, amazingly, if you have a higher power consumption, this can in turn still result in a lower overall energy consumption if you just consider a certain task to be performed. So if you look at the diagram on the top right-hand side, you see that we have a task that is first executed at a certain lower frequency, which is the gray shaded area. And at a lower frequency, it takes our processor longer to execute that task. Now the energy is the integral over time. So if we take the integral over the time, until our value t0, well, we have a certain amount of energy. Now, if we manage to clock our processor a bit faster and it finishes significantly faster, uh, then in turn we have a higher power consumption during the calculation this processor performs. But since we're already finished at time point t1, we might in the end use less energy than running at a lower frequency. So it's not as simple as I clock my processor as slow as possible, and then save the most energy, but it really depends on which tasks you can do. And of course, when your processor has nothing to do, then we need to ensure that we're able to turn the processor off to save as much energy as possible. However, no matter what, if you have higher power consumption, if you use more power, then In turn, this results in higher heat dissipation, so this might be a problem for some applications here. So energy consumption trends. Well, you see, the interesting thing is we have a diagram here that shows on the x-axis the progression of time in years, and on the y-axis we see how much computing power per amount of energy, so per joule, is available in a system. And you see this is continuously going up, so from year to year we manage to increase the amount of computing power, so the amount of computational operations per amount of energy. But the interesting thing here to see is that we have more or less three distinct lines here. So, and the fourth in the middle. So the lowest line with MPU written next to it is our traditional microprocessors and microcontrollers. So as we can see, these are relatively energy inefficient because they have to execute everything in software. So software is relatively slow. Then we have specific hardware on top, like FPGAs. FPGAs are programmable logic chips, so we can implement parts of an algorithm in parallel hardware. This is specific hardware, so we don't need to fetch instructions, for example, to execute an algorithm, but all of this is already integrated into hardware. So this can be much more efficient, and we can build custom chips, so-called ASICs, application-specific integrated circuits, and these are even more energy efficient. And we have something interesting in the middle, the so-called DSPs, digital signal processors. We've seen signal processing before when we looked at sensor data, so digital signal processors are microprocessors which are optimized for running operations on digital signals like filters, like Fourier transforms, and so on. So they have special acceleration instructions for this, like multiply and accumulate instructions, maybe even special data formats. So similar to what we've seen in our security chapter, where we had essentially specific applications to accelerate cryptographic algorithms like AES or SHA. Here we have specific instructions that can be added to our program, which make very common operations like a multiply and accumulate and digital signal processing more efficient. Now, what's interesting to see is that there's always about an order of magnitude, so a factor of 10 or more between these. So if I run certain kinds of applications on a DSP, I can be 10 times more energy efficient as running it on a microprocessor. And again, if I run it on FPGA, I can be again 10 times more energy efficient. And if I manage to build a custom chip, which only makes sense when you build millions and millions of them, then I can again be a little more energy efficient. So essentially what we do in the IoT, running everything on microcontrollers, might be the most energy inefficient way, but of course we have other non-functional concerns that we have to consider, like cost, for example, and maybe a microcontroller is the most cost-effective solution there. So how do we measure power? How do we actually find out how much power at a given moment is consumed or dissipated by a device? Now, we've seen the electrical power is equal to the supply voltage times the current flowing through a conductor here. So we can measure this by inserting a shunt resistor into the supply voltage line. This is a highly precise resistor which has a resistor with a very low resistance. So this resistance has to be very low in order not to decrease the supply voltage significantly, but only by a few millivolts. And this sits in the power supply line of the semiconductor we want to measure. So the semiconductor, we are interested in its power consumption here. And this semiconductor or this device we want to measure is usually just modeled here as the purple load resistance R load. And the assumption we take is that the supply voltage provided by the power supply is constant, for example, 3.3 volts. So we have one part of our power equation constant, the U, with 3.3 volts. So in turn, we only have to measure the change of the current over time, and then we can take a look at the power consumption of our device. And of course, people did this. So Steinke and Knauer did this in Dortmund in Germany. So they built one of the very first useful energy models for embedded computers. So you see their experimental setup on the top left-hand side. This is an Atmel board with an early ARM7 microcontroller and ARM7 TDMI. And this, compared and contrasted to modern microcontrollers, still has external SRAMs, which makes it very convenient for this sort of application because then we can actually measure the impact of the CPU power consumption and the impact of the RAM power consumption separately. Modern microcontrollers integrate the SRAM onto the chip, so there we don't have separate power supply lines anymore for the SRAM and the CPU. So for modern microcontrollers, we can usually only measure the overall power consumption and not do it separately. So the interesting thing is now we measure two currents, so the current supplied to the CPU and the current supplied to the RAM, and derive the respective power numbers from these currents. And Stanke and Knauer found out that the overall energy consumption can be derived from the instruction and data accesses, which take place in the CPU and which affect the memory. So the overall or total energy consumption of this ARM7 consists of the energy, uh, that we need to invest for executing instructions in the CPU, the energy for reading and writing data in the CPU, and the same on the memory side, because instructions and data reside in memory. So whenever a CPU starts to execute an instruction, it has to be fetched from memory, transferred to the CPU, then the CPU starts executing it, and eventually, as a result of executing the instruction, it reads more values from memory or it writes the result into memory. So the interesting thing here is we have two optimization opportunities. We can optimize on the CPU side and we can optimize on the memory side. And in the next lecture, we'll see some examples of how to do optimizations on both sides. So Stanke and his colleagues derived a relatively complex model to model the energy, which is instruction dependent. So it's not just the CPU running at a certain frequency, but we take a closer look at which machine instructions are executed by the CPU, and we can try to figure out what the impact of executing a single machine instruction is, and actually also a single machine instruction operating on certain data. So here's just an example from their cost model. Please read their paper if you're interested. So the cost of a sequence of M machine instructions for just the CPU instructions is the cost of actually executing the opcode plus the cost of switching the function units. So if we have, for example, an addition followed by a branch, we need to switch between these units in the CPU, and then all the other impacts of parts of the instruction flow. For example, if we have certain immediate values, if we have to switch between immediate values, if we use certain registers and switch between certain registers, if we have certain values in a register and switch between these values, and also if we have certain addresses and switch between an address and the subsequent addresses. And so all these influences, the number of one bits indicated with a W here, these can be counted, these can be determined by tracing the execution. So we actually look at all the instructions executed one after the other in the CPU. So W is the number of ones, which means the number of ones in, for example, an immediate or a register is important, but also what we call the Hamming distance. So the distance between 1 and 0 bits overall between a value and the next value in a register is important. So these are the components on the left-hand side of the sum and on the right-hand side of the sum, and these are weighted by parameters alpha and beta. And these alpha and beta are what was actually determined by executing specifically prepared amounts of code on this ARM7 platform here, and then measuring the respective power consumption to, in turn, backwards derive all these parameters that make out our model. Of course, these parameters are only valid for this specific chip. So if we use another ARM7 TDMI, which might have another internal circuit, then we'd have to do all the measurements over again because this chip might have a different ways to, for example, do additions. So there are different ways to build adders in semiconductors. And so in turn, the energy consumption would change. So we need to characterize at least a certain type of chip. And if we want to be very precise, we might even want to characterize a certain uh, yeah item of a chip, so one single chip that we have here on our desk. We can also have other costs like data-related costs. So the previous slide only considered instruction-related costs, but we have several things about data. For example, where data is in memory, so the address of data, the value of data, and how addresses of subsequent data items and the addresses of subsequent and the values of subsequent data items actually change between one instruction and the next instruction that's executed. And so these all contribute to our overall energy consumption of our system. So the question we need to ask ourselves is, which are the most important software effects actually that influence power consumption and, of course, in turn, energy consumption? So we've seen that software behavior can influence and does influence the switching behavior of a circuit. So, for example, if we add two numbers, and these two numbers are both zero, of course the result is zero. So if I add 0 to 0, like you did in school when you learn addition on paper for the first time, you add each digit separately. And if you add a 0 to a 0, the result is always a 0. So there's no bits flipping. You don't have bits flipping from 1 to 0 or the other way around. Now consider adding two bit strings which consist solely of 1 bits. So for each bit you add 1 plus 1, and now we're calculating in binary, so 1 plus 1 is 0 with a carry of 1. So if you add two ones, you have to flip a bit somewhere to produce a 0, and then you have to switch a carry bit to a 1, which is much less energy efficient. So we have relevant effects, which is the so-called Hamming distance between adjacent memory addresses, but also adjacent values of data that's being operated. Now this model is far too complex to discuss it in very much detail here, so I would love to relate you to the respective paper of Steinke and his colleagues here. It's just interesting. We show some two diagrams of the influence of the Hamming distance on the current and in turn obviously on the power consumed by our ARM chip here. So Steinke already found some results, and these results are already a couple of years old, and there's more recent research on this, which we can't also summarize here because it's getting more and more complex. So Steinke found out that it's not actually important which bits of an address are set to 1, but just how many bits on the address are set to 1 is also not relevant. The cost of flipping a bit on an address bus is independent of at which bit this bit actually flips, so it's just the effect that a bit flips from 1 to 0 or the other way around. It's also not important which data bits are set to 1, and the number of ones on a data bus has only a very minimal effect of around 3% on the power consumption, and the cost of flipping a bit on a data bus is in turn independent of the bit position. So we have some effects which actually contribute to our power consumption, some effects which don't contribute to our power consumption, and some effects like the number of ones on the data bus, which only have a very minimal contribution here. And from this, you can build an energy model where you can input a piece of machine code, and then you can simulate that machine code, and you don't only get the functional result, for example, the number that was calculated out, but in addition, you get an information. When you have this model attached to a CPU simulator, then you get this information like this piece of code executed in that way consumes so and so many nanojoules of energy. And if you have this information, then you can use this to optimize energy, for example, in a compiler backend, as we'll see in the next lecture. So there's, as I mentioned, much more research on energy modeling and energy analysis. It's still an active research topic. So very first simple models were invented by Tivari for energy consumptions within processes only. Diana Simonic used values from data sheets to model energies, and she tried to model all components in a system, not only CPUs and memories, but not very precise. Russell and Jacome had measurements for two fixed configurations. The Steinke model was improved by a mixed model with predictions. And then we have two tools which are very useful today. So we have the Cacti tools, which can model CPU caches related to energy consumption. And we have the Watch tool, which is a power estimation at the architecture level of a semiconductor. So this is on a higher level, so you don't have to have an implementation of a circuit or layout. This in turn might be less precise, but is much faster and more independent from your specific chip that sits on your desk. So after learning about how to actually analyze the energy consumption, of course, we need to figure out where all our energy comes from. So we've already noticed that very many IoT devices are not connected to a permanent power source. So this means they have to rely on other energy sources. And this can be just non-rechargeable batteries. These usually have a low capacity, are expensive, and might cause environmental problems because they might, for example, be dependent on the procurement of rare earth materials from the ground, which are often produced under not very environmentally friendly conditions. So an alternative to this is to harvest energy from the environment. So energy harvesting means that we use some sort of physical effect that's out there, which is all energy, no matter if it's mechanical energy, for example, and we try to convert this energy into a form we can use, so into electrical energy. And there's quite a number of physical effects that can be used, and you've probably seen a number of them. So photoelectric effects, so light. Of course, that's what flowers and plants also do, and we can also do it in photocells. So we can convert photons coming in to a surface to a flow of electrons, which is a current. We can use piezoelectric effects like mechanical strain to generate electric energy. We have thermoelectric generators here that rely on temperature difference. We can use kinetic energy, so movement. This is one of the oldest forms, obviously, of obtaining energy. For example, using this to recharge a mechanical watch by either turning the watch knob or by having one of the more modern mechanical watches that you just need to shake on your arm in order to recharge it. Of course, in these mechanical watches, it's just a conversion of one form of mechanical energy to another form of physical energy, usually not electricity. We want to convert kinetic energy, obviously, to electric energy. And finally, of course, nowadays we have electromagnetic radiation all around us, from wireless networks, from radio and TV transmitters, from your home Wi-Fi, and whatever you can imagine. So even though this is relatively weak, nevertheless it's energy that's being transmitted. So there are some chips which actually make use of this electromagnetic radiation that's all around us, take a little bit of it, and use it to power themselves. So here's some examples for energy harvesting. The first one is a thermoelectric generator. And this actually uses ambient solar energy to convert temperature differences across a material. So for example, if you have a piece of material that's on the sunny side on one side and in the shade on the other side, you know that you have a temperature difference. The temperature difference means we can extract energy from this, so the temperature difference across this material from the hot to the cool side can be used to generate an electric current. And this can actually result in a steady voltage even when the difference in temperature remains unchanged across the chip. A different way to harvest energy is piezoelectric energy harvesting. So this relies on mechanical stress of a component, so mechanical stress of a certain piece of equipment. And if we apply this mechanical strain to this component, we can also extract, using this piezoelectric effect, energy from this. This is the same effect that's used in the other way around in clock generators for processors. So these also have a quartz, and this quartz uses a piezoelectric effect when just provided with some electric energy, and then it starts swinging, and the quartz swings at a certain given frequency dependent on its crystal pattern, and then we have a reliable clock source for our processes. So piezoelectric energy works both ways. And you can use, for example, vibrations from low frequency vibrations like acoustic noise, human motion, and so on to generate electricity using piezoelectric generators. Another important or interesting example is what I already mentioned, the ambient electromagnetic radiation harvesting. And there's a company in Oslo and Trondheim called Onyo, and they have developed the Onyo Zero chip. This is a 32-bit, very small and simple RISC-V based microcontroller, which has very little hardware features, so only 1 kilobyte of ROM, which contains a number of standard library functions for mass, for I/O, and so on, 2 kilobytes of RAM, and a bit of ultra-low power flash for your application. And this has an internal radio frequency rectifier, so all the radio frequency hitting this chip coming from the environment can actually be converted into a power source for this chip using this rectifier. And you can actually have this rectifier work on several frequencies. And of course, this is tuned to the most common frequency of electromagnetic radiation around us. So the different wireless frequency bands, so ISM and GSM bands for our mobile phones, so 800, 900, and a number of additional frequencies, including the 2400 megahertz ISM band, where also Wi-Fi and Bluetooth is located. So this can also have internal power generation. So if you decide to instead provide this chip with solar energy, it's perfectly fine to have very low power or low voltage solar cells that only provide 400 millivolts, or even piezoelectric and thermal voltages. And these converters here on the chip are all able to supply voltage power to the chip. So this chip is very versatile. You can operate at a voltage as low as 450 millivolts up to 1.8 volt. And of course, it cannot be very fast because it needs to conserve energy. So it can run up to 24 megahertz, but it can also run in an asynchronous mode where it doesn't even need a clock. So this is an interesting chip. The downside to this is there's announcements, there's maybe a data sheet, but I haven't seen any real instance of a manufactured chip so far, so I'm not sure if it exists. Let's find out. Now, if you harvest energy, the problem is that energy is not always exactly available when you need it. So essentially, the sun shines usually, for example, if you want to power street lamps with solar power, then you have a problem because when the sun shines, you don't need a street lamp. And when you need a street lamp, the sun doesn't shine. Well, that's a very obvious problem. So you have to store that electric energy somewhere when you collect it. So yes, how can we do this? Now, there's two major ways to store electric energies. One is, I'll start with low one, rechargeable batteries. So the same thing you know from your mobile phone and every other device that can be recharged usually. So these rely on chemical processes, so there's a limit to the number of cycles a battery can be recharged. And you know when you operate your mobile phone over several years, the capacity of your battery goes down and down, so it doesn't hold as much capacity after a couple of years than it did initially, because some of these chemical processes inside the battery break down, and eventually you have to either exchange the battery if you can do it, or throw away your device if the battery is just glued in and not replaceable. So rechargeable batteries are useful for some applications because they have a high capacity, they're relatively cheap, but of course they have a limited lifetime. And an alternative to rechargeable batteries are large capacitors. So large capacitors can be charged very, very fast compared to batteries, which take quite some time. They can have very high output currents if you need them. They're close to 100% efficiency, so there's almost no loss. So almost all the energy you store in a capacitor you can retrieve afterwards. You have very low leakage currents for high quality capacitors. So there's a special sort of capacitors which is called gold caps because, well, it has a gold cap, so a cap made of real gold, which is very useful but also quite expensive. And you can have an almost infinite number of charge and discharge cycles for a capacitor. So this might be very useful for long-running devices that have to operate for years or even decades. Now the disadvantage is capacitors have a relatively small capacity, so they cannot store a lot of energy, which means that, you need to reduce your energy consumption. And of course, as I already mentioned, we'll look at how to reduce energy consumption in the next lecture. So here's another example of energy harvesting, and this is from a PhD thesis from Imperial College London. And this was the idea to use rotational energy as a source. This is nothing new. That's something that's already used in mechanical watches and so on. Here we use low-frequency broadband rotational energy harvesting for self-powered sensing solution in medical applications. And this includes an electromagnetic, piezoelectric resonant, and a piezoelectric non-resonant energy harvesters. So we're combining a lot of the technologies we've seen before here. Now, the important or interesting thing is, well, first you see the mechanical structure, which is quite complex on the top picture, but the interesting picture, the more interesting picture is actually the one on the lower side here. So if you look at the left part of the diagram, you see the charge cycles, and these charge cycles are given in minutes, so more than half an hour required to charge a device. And then you look at this very small part where the line almost goes vertically down, and this is actually then enlarged on the right-hand side. And you see this is a discharge cycle, and this discharge cycle, excuse me, well, is a couple of seconds. So all the energy you harvest here is so minimal that even harvesting energy for half an hour only allows you to operate the device for a couple of seconds. But if you only need a measurement point every couple of minutes and you're perfectly happy that, well, your software only can run for 2, 3, 4 seconds, then that's perfectly fine. The big problem is how to actually ensure that between these phases without energy consumption or without energy availability, you store certain values that you need for your next phase of operation. And this is what we call intermittent computing, and this will be the topic of the last lecture of the third lecture on energy consumption in the IoT. So today we've looked at energy modeling, energy generation by energy harvesting, and we've seen that energy consumption and energy generation both are one or two of the central problems of IoT nodes. We can model power and energy consumption of software nowadays with relatively high accuracy, and we've seen that the energy to operate IoT nodes can often be harvested from the environment. This exploits physical effects to convert other forms of energy, like mechanical energy, into electric energy, and we need some storage of the energy because very often energy is not available when we need it, but at other times. So we need to store it until we actually make use of it. And we've also seen that often recharging takes significantly longer, so orders of magnitude longer than the discharging. So this means we have to live with the fact that for very many applications using energy harvesting, only very little energy is available for performing our actual task, maybe a couple of seconds, maybe even less. So we have to build our applications so that they can cope with this. So this was our first lecture on energy, about energy modeling and energy harvesting, and we'll discuss more details on energy optimization and intermittent computing in the upcoming two lectures. So as always, here are some references for you to look further into if you're interested in details. So thanks for listening, and until next time. Bye.